Well, thank you very much for the introduction. Thank you very much for inviting me. It's great to be here for Frank. Yesterday I was thinking about what to say. It's not that it's difficult to say good things about Frank, but I thought I should ask my new friend ChatGPT to say something. So here's what I got. So ladies and gentlemen, distinguished guests and fellow colleagues, it was with great pleasure and honor that we gather here today to celebrate and pay tribute to the remarkable contribution of a true mathematically visionary Frank Mel. As we delve in the realm of analysis and dispersive equation, we stand in awe to the extraordinary mind that has illuminated the field with profound insight and so on. Anyway, it goes on like this. And then I asked actually for an anecdote because I thought I could get one which will be fit for the occasion. So here's what I get. So once upon a time, during a particularly intense mathematical conference, Frank Mel found himself lost in thought, deep in the intricacies of complex proof, oblivious to his surroundings. He absent-mindedly started scribbling equations on the back of a napkin during the coffee break. Unbeknownst to Frank, his napkin quickly caught the attention of an unsuspecting waitress who mistook his calculation for an avant-garde artwork. Thinking it was some kind of...
You are joking, right?
I don't know. This is what I got from ChatGPT. I mean... So his napkin quickly caught the attention of an unsuspecting waitress who mistook his calculation for an avant-garde work, thinking it was some kind of sophisticated abstract masterpiece. She snatched the napkin and proudly displayed it in the cafe art gallery. Is it true? So weeks later, as Frank wanders through the streets, he stumbled upon the very same cafe and noticed a familiar piece of paper hanging on the wall. His eyes widened in disbelief as he recognized his own mathematical equation masquerading as art. Frank couldn't help but chuckle at the absurdity of the situation. Is it true? I mean, it was on ChatGPT.
Okay, based on thought.
Anyway, so it goes on like this. So, well,
Okay.
it's really a great pleasure.
Let me have a
All right. Okay. So I will be talking about the stability, the nonlinear stability of Kerr, rotating Kerr black holes. This is work in collaboration with J Szeftel and some others, as you'll see it in a moment. Here is. I go directly to the conjecture, and I'll try to explain what the picture means. In any case, the conjecture says the following: Einstein vacuum, asymptotically flat perturbations of a given exterior Kerr solution for A less than m have maximal future developments converging to another Kerr solution. So the story, so let me explain the word. So obviously Einstein vacuum means I'm looking at space-times, 3 + 1 dimensional, so this is a Lorentz metric such that the Ricci of G is equal to 0. Right? So this is a nonlinear equation. One very important thing which I will play a role in our discussions is that a solution of the equation is a Lorentz metric up to diffeomorphism, right? So I'm going to identify G and phi star of G for any phi being a diffeomorphism of the manifold, right? So it's a large group of transformations which keep the solution the same. I mean, you're talking about the same solution whether you write it in one coordinate or another. And the Kerr family, so this is a Kerr family of solutions which depend on two parameters, A and M. So M represents the mass. This represents the angular momentum. So this is a family of stationary solutions. So in some sense, that means that they are time independent in a certain way, which will make precise. And they are also asymptotically flat, meaning that look far away from a compact set. They look like Minkowski space. So Minkowski space being, of course, the simplest possible Lorentz metric. So what else shall I say about this picture? So this is the picture of the Kerr solution, okay, that you see here. there is actually a part that one can discuss a part in the past. So the future is represented by this direction. It's a compactified picture in the sense that this boundary here is actually at infinity. There is a parameter r, which measures the distance, let's say, to the black hole. And here r is equal to infinity. This at everything at 45 degrees corresponds to null characteristic directions. R equal R plus, I'll say in a moment what R plus is also a hypersurface, a null hypersurface, which represents the boundary between what is called domain of outer communication, which is this one, which looks like Minkowski space in many ways, and the black hole region, which is here. So once you are in the black hole, you can never get out, and so on and so forth, right? So you can say you can spend a lot of time on this picture. But the important thing is that my Kerr solution is given, and I have a space-like hypersurface here, and I'm looking at the Kerr solutions. So in other words, I look at the induced first and second fundamental form of the Kerr on this space-like hypersurface, and I perturb it a little bit. Right? So I make a perturbation, and the perturbation, of course, has to satisfy itself, some constraint equations. I'm not going to get into that. But the important thing is that small perturbations will lead to a new solution of the Einstein equations. So it will be a new solution of these equations, which will look in the future of the space-like hypersurface, will look quite similar to the Kerr solution, except there will be a difference, is a new Kerr solution. So the perturbations converge to actually a new Kerr solution. And of course, that's another thing that plays an important role, because a priori you don't know what will be the final parameter. You start with parameter A and M, and you don't know what the final parameters are going to be. Right? So the results that we have, which are results with J Szeftel, few papers with him, and also a paper with Elena Giorgi, and there is an independent paper by Shen, which together give you a proof of the conjecture for the particular case when the angular momentum is sufficiently small. Okay, all right. So that's the result, and here just a few facts about the Kerr solution. So again, these are stationary asymptotically flat solution of the Einstein vacuum equations. Obviously, the simplest solutions, which are part of the Kerr family. So when A is equal to 0, M equal to 0, you get Minkowski space. So this is a space which was introduced by Minkowski in 1907. Schwarzschild, 1916, actually. I keep having this mistake. Anyway, it's a case when A is equal to 0 and M is different from 0. So it's a non-rotating black hole. And finally, the full family was discovered in 1963. And this was an amazing discovery, right? Because it's just a stunning family, explicit family of solutions of a very complicated equation, Einstein equations. All right, so this is how the Kerr solution looks in a system of coordinates. It's not too important for us, but at least for once it's good to see how the solution looks like. So this is the amazing thing is that this is an explicit solution of the Einstein equations. You see the coefficients here are given in terms of these parameters. So you see R, A, M. So R, I talked about it. It's somehow the distance to the black hole, if you want, in the simplest possible way. And everything, as you see here, is very concrete, right? Expressed in terms of these coordinates, TR, theta, phi, which are similar to the spherical coordinates, if you want. In the case of Minkowski space, this will be, of Minkowski or Schwarzschild, this will be exactly the polar coordinates, the standard polar coordinates. Anyway, this is stationary. The stationarity of the solution just simply means that all the coefficients that you see here do not depend on time, right? So that's very easy. But it's also axisymmetric in the sense that they don't depend, the coefficients don't depend on this parameter phi. So that's so it's both stationary and axisymmetric. There are two killing vector fields, in other words. This is d over dt and d over d phi. It's asymptotically flat, as again you can see it immediately by taking the coefficient, by taking r going to infinity. All the coefficients go to the coefficients of Minkowski space. That's what asymptotic flathead means. There is something important algebraically, by the way, very much like algebra. So algebraic calculations are extremely important in all this. There is a remarkable algebraic fact that there are two vector fields, E3 and E4. Maybe I'll say a few more words about it, which are null vector fields. So null simply means that G3 is equal to 0. By the way, in Minkowski space, if you are in Minkowski space, maybe it's worthwhile writing what they are. So E3 is dt plus minus dr, and E4 is dt plus dr. So they are both null, they form a null pair, and they're extremely important because they give you the propagation properties of solutions of wave equations, and in particular also the Einstein equations. The remarkable thing about these vector fields, E3, E4, which are sort of variations of these ones for the Kerr solution, is that they diagonalize the curvature tensor. So the curvature tensor could be quite complicated. So there is a Riemann curvature tensor, which could be quite complicated. But if expressed relative to this frame, everything is zeros except two terms on the diagonal. Let's say if you want on the diagonal, whatever it means, if you write it as a matrix. Okay, so it reduces, instead of having 10 components, normally you have 20 components. You have 10 here, which is the equation. So you get 10 left. Out of those 10 left, only 2 are different from 0 relative to this frame, right? So it's a remarkable algebraic fact which plays a fundamental role. Another thing which is important, it's also algebraic fact, is that in the case of A is different from 0, the space orthogonal to E3, E4, which we call it an horizontal structure, is non-integrable, right? So it does not. So this is in the case of Minkowski space, if you look at the space orthogonal to E3, E4, you get exactly the spheres are equal constant, right? So these are integrable surfaces. Schwarzschild, the same thing. You get integrable surfaces, but it's not true in Kerr. Okay, so that's something that leads to sort of important conceptual differences in the way Kerr solution is treated relative to the Schwarzschild solution. Okay, so what are the main difficulties? So again, this is a picture. That's what we want to solve. We want to start here and to go to the future. So this is the Einstein equations to start with are strongly coupled tensorial, quasi-linear, right? So and hyperbolic. So you get the worst of all possible words if you want. It's hyperbolic, it's tensorial, right? And of course it's quasi-linear. Another major difficulty, which I mentioned, is that it's this huge diffeomorphism group, right? So a metric is really a class of equivalence of metrics up to diffeomorphism. So this works in both ways. In one sense, it's an advantage. In another sense, it's a disadvantage. But it's only an advantage if you know how to use it, right? As we shall see. Now, the non-trivial nature of Kerr, well, you see it here. This is a Kerr solution. By the way, this R equal R plus, I think I said something, so maybe I should go back. It's nothing else but a root of this polynomial, R squared plus A squared minus 2mr. Anyway, so this is, there are all sorts of complications about the space-time. Of course, there is a black hole. Now, the conjecture doesn't really say anything about what's happening inside when you perturb. And in fact, there are lots of very interesting problems that have to do with what the behavior inside. You get singularities. Anyway, but it's a totally different story. I'm interested only in what happens in the exterior, right? So up to a horizon. So to solve the Kerr conjecture, you really have to solve the Einstein equations up to the new horizon that forms. But it's not, you don't know the horizon a priori. So when you do a perturbation, you don't know where this will going to go. It's only, it's a teleological quantity that you see only after you have solved the full equations, you get the horizon, right? So in reality, when you solve it, you have to go a little bit beyond the horizon. You cannot stop at the horizon because you don't know where the horizon is, right? All right, so control the Cauchy horizon? No, no, not at all. We don't say anything about the Cauchy horizon, right? So that's a totally different problem, right? It's also interesting, but it's a different one. So it's non-trivial nature of Kerr. There is more to say. There are lots of things to say about it. Even solving the wave equation, as we shall see, I'll say a few words about it. Even solving the wave equation scalar with a scalar phi here equal to 0, it's a highly non-trivial problem, and it was only understood in the last 20 years. Okay. So what are the final parameters? You don't know what the final A and M are, right? So this, you cannot determine it from the initial data. It's only a posteriori that you know them. But even more difficult is the issue of the fact that the convergence to the final state is gauge dependent. In other words, you don't know a priori what gauge to pick which will lead to convergence, right? So you actually, even the gauge that the final gauge in which you have convergence is only determined a posteriori, okay? So that's one of the major problems, in particular since it's an infinite dimensional thing. I mean, right. Anyway, so the final parameters and the correct gauge therefore emerge in the limit. Another major difficulty, which of course we know for people who work in nonlinear hyperbolic equations or dispersive equations know very well, you only have some dispersion, some dispersive, which leads to time decay, but those are very, very slow. And the decay is extremely important. And by the way, the decay is heavily dependent on the gauge that you pick, right? So even if you take the wave equation in Minkowski space, you know that it decays in time. If I pick up a different system of coordinates, I have no idea, right? So these issues of decay are heavily gauge dependent, right? So, and again, it's all part of the same thing. So obviously, the biggest problem of all is that you have to solve all these issues at the same time, okay? You cannot separate them, really. I mean, fortunately, we have ways to separate it by bootstrap assumptions, but that also requires that you understand the full problem. Anyway, here is just a fast recall about properties of the wave equation in Minkowski space. So this is just the wave equation in Minkowski space. Of course, we know that we have energy conservation. We know that we have pointwise bounds for an infinity norm. This is actually not quite correct what I wrote here. Sorry, this is energy. Pointwise bound for the energy. It just follows from the conservation of energy. Pointwise decay, then infinity norm decays like t to the minus n minus 1 over 2, n being the dimension. So if you are exactly in R1 plus 4, this is very little. It's just t to the minus 1, which obviously can lead to lots of difficulties. And in fact, we know for nonlinear perturbations of just the wave equation, for example, if I put something here, which is dt of phi squared, this does not have global solution even for small initial data. Okay, anyway, so an important thing that is used in nonlinear equations today, and certainly it's used by us, is a vector field method. In Minkowski space, this simply means that you identify these null vectors. It's a null pair. And then from it, you form a null frame. So these are exactly these ones here. They are intimately tied to this u equal t minus r and u bar equal t minus r, which are characteristic hypersurfaces, right? So they represent cones like this. So if u is equal to 0 or constant, or u bar is equal to constants, this would be a cone in the opposite direction, right? So the important thing about the vector field method is that using some vector fields which have good commutation properties with the wave equation, you can derive decay estimates from the energy estimates, right? So that's there's no reason to say anything more. Maybe I should say another very, very important thing is that different components of the different directions give you different decay, right? So you can see here, this is in n dimension. In n dimension, psi will decay only like t to the minus 1. If you take, however, derivative in the e plus direction or e4 direction, this I also call it e4 here. So you get better decay. You get decay to the t to the minus 2, but the same thing happens with angular derivative of psi. You get decay also at e to the minus 2. And the only component which is badly behaved is a transversal component to the null cons. Okay? And this decays still like only to t to the minus 1. Anyway, the precise decays are given in terms of global Sobolev type inequalities. Right? All right, so this is just a quick review, but it's important because obviously these hypersurfaces and these frames are going to be very important. Okay? In particular, I mentioned that in Kerr there are certain similar type of vector fields like here, but they lead to non-integrable structures, but they have the properties that they diagonalize the curvature tensor. And of course, there is something, the null condition, which also plays a fundamental role in all these issues. This is based on the notion that somehow the nonlinear terms are combinations between good derivatives and bad derivatives, right? All right, so here is something that everybody in this audience knows very well, so I'll go very fast. There are different types of stability, right? So the global stability problem, we have a nonlinear term depending on phi. You assume that you have a stationary solution, let's say, which is this one. You make a perturbation. You get something which is called orbital stability, which means that psi stays bounded for all time of size epsilon. Asymptotic stability, which means that actually psi actually goes to 0 under perturbation. And something that I like to call orbital asymptotic stability, although Jeremy tells me that's not a good definition, but anyway, I like to use it, which means that phi 0 plus psi converges, but converges to something different, a different solution, a different stationary solution of the original equation, right? And this is, of course, the situation that we are in, right? Because instability of Kerr. Now, you look at the linearized equations, so obviously the first thing that you do when you have a nonlinear problem. And here you have also various definitions of stability. You have the mode stability, which means you look at the linearized equations and you decompose it in modes, right? So you do the spherical harmonics or whatever separation of variable method you have at hand. And you prove that none of the modes are growing. So no growing modes is one form of stability. But of course, no growing modes is very far away from showing that solutions of this equation under perturbations remain boundless. So even the first one is very, very weak. It doesn't even include boundless. But boundless itself does not include quantitative decay. You get decay, right? As we discussed for the wave equation, I need decay rates in order to be able to prove anything nonlinear. And then there are various versions of decay also. You can have some quantitative decay, but you can have very little. Suppose you have a nonlinear problem and you prove only, for the linearized version, you prove only t to the minus a half instead of t to the minus 1. There are lots of results like this because already to study the wave equations in Kerr is already very difficult. So even at the beginning, people were happy given to prove some kind of weak type of decay results. So anyway, so there are results, and then there is something that I would like to call optimal quantitative decay, which means something which is at the level of what to expect for Minkowski space, which is, say, t to the minus 1 and maybe various other facts about decay in the interior and so on and so forth. Because for the wave equations, you have decay along the null cons, which is the worst kind of decay, but you will have better decay in the interior. Anyway, so all these issues go under the name of optimal quantitative decay. And obviously, mode stability does not imply boundedness. Boundedness does not imply quantitative decay. Quantitative decay does not imply optimal quantitative decay. And of course, optimal quantitative decay does not imply this, which is a nonlinear problem. I'm saying this because there is a lot of confusion, not only in the physics community, but even among mathematicians, that somehow, if you prove linear stability, that's kind of enough to then do nonlinear stability, and that's just wrong. Okay. Anyway, so let's go on. In the case of the Einstein equations, what happens is similar. This is your nonlinear problem. You linearize around Kerr, so this is a Kerr solution, and you get this kind of complicated linear system. So delta G represents linear tensors, if you want, and the general covariance, which you have at a nonlinear level, now becomes something at a linear level, which means that you identify two solutions of the linearized equation that identify up to arbitrary Lie derivative of vector fields of the Kerr solution. Okay, so this is something, again, a very simple calculation that everybody here knows. But in any case, the important thing is that, again, you have a huge kernel here, right, which is infinite dimensional. And obviously, modulation theory, we owe to the French school, and Frank has done a lot about it. The only sort of new difficulty here is that it's an infinite dimensional situation, and it's highly tensorial, and so on and so forth. Right? All right, so we need to do some kind of modulation in infinite dimension. So let's talk now about some history. So first of all, discovery of Kerr, as I said, this was an amazing discovery. I would think I don't know if Thibault agrees, it's one of the major discoveries of the last century in physics. Linear mode stability, there was a perturbation for linear theory. So this is linear mode stability. So the physicists typically did just linear mode stability initially. They didn't have actually the techniques to do the full spiel that I mentioned earlier, but they did a lot of very interesting things. Like, for example, there is a Regge-Wheeler equation, which is discovered at the level of metric perturbation. So, I mean, this is something important. You can do metric perturbation. In other words, you can look at this equation and do G plus delta G directly. Or you can look at the Riemann curvature tensor and do perturbations at the level of second derivative of the metric, which is at the level of so this is called the curvature perturbation, right? Which was developed later in the 70s. There are lots of people also, but I just mentioned Teokolsky. So this is Teokolsky equations in 1973. This is an extremely important equation that Teokolsky discovered, which plays a very important role in what we do. And then there is another sort of very important thing that was done by Chandrasekhar, which is called the Chandrasekhar transformation theory, which connected this metric perturbation to curvature perturbation, again at the linear level. And it's exactly this Chandrasekhar transformation, which was, as we see, was used later on by mathematicians, in fact. So now there are other names to be mentioned here. There is Whiting in 1989, which studied the mode stability of the Teokolsky equation. And then more recently, the full linearized equations in mode stability for the whole linearized equations was done by Anderson, Hefner, and Whiting. Right? Global stability of Minkowski space is number 3. So this is my work with Christodoulou in 1993. The important thing here was development of the vector field method, a null condition played a major role, and so on and so forth. But I am not going to talk about this. Kerr stability. So now, what are the important steps on Kerr stability? So first of all, you needed to do robust meaning not using modes, not using mode decompositions, but actually proving direct decay estimates for solutions of the wave equation. So first of all, the Schwarzschild case A equal to 0, m larger than 0. This was done by starting with work of Sofer and Blue Sofer and Blue Sterbens, so many people who participated in this. The first major result, however, really goes to Sofer and Blue Sofer, who really just changed the direction of the field, because we were all trying to do something very different until they did what they did. Then for A small, there was Dafermos Rodniansky, Tataru Tohoneanu, Anderson Blue. These guys did boundedness, and they were the ones who did decay. Anderson Blue used a method, which is in fact the method that we are using today. So I'll mention maybe at the end if I have time. The case, all the way up to M was done by Dafermos, Rodniansky, and Schappeter-Rothman. And again, it was based on a combination of vector field method and mode decomposition. So it's heavily dependent on mode decompositions, so it doesn't easily adapt to the general case, but maybe it can still be adapted. But the general case meaning general perturbations of Kerr, right? All right, so then there is a Teokolsky equation. So Teokolsky equation is a spin 2 wave equation. So it's more complicated than this. It has additional terms on the left-hand side. I'm not going to get into it, but it's much more complicated. And the first results of this type were due to Dafermos, Holzegel, and Rodniansky, where they used this Chandrasekhar transformation. So this was a very important step in the whole process, to use the Chandrasekhar transformation to get that. Then this was extended later on to A less than M. So this was done by Ma and later by Dafermos, Holzegel, Rodniansky. And this case, which corresponds to this one here, was done by Millet and Schlappenthal, Rothman, and Da Costa. So this is a postdoc now at Princeton. Anyway, so then linear stability. So this is still at the level of just one equation, right? It's a spin 2 equation. Linear stability was then done by the linear stability for the entire linearized gravity was done by Dafermos, Holzegel, Rodniansky in 2016. And then there were many other works in Kerr. These are Anderson, Bagdal, Blue, and Ma, Hintz and Bassi in 2021. This is for slowly rotating, the slowly rotating case. Again, all these decay estimates, they are proving decay estimates in all these cases, but they are clearly not enough to apply to the nonlinear case, right? So these are examples of what I said earlier, that linear stability is far from nonlinear stability. Then the next big thing was nonlinear stability of Schwarzschild in the polarized case, which was done by Jeremy Szeftel and myself in 2019. This was, we used the polarization assumption. Oops. Excuse me. Maybe I should keep it in my hand. We used the polarization assumption, and a more general result was proved later by Dafermos, Holzegel, Rodniansky, and Taylor in 2021. There are lots of things to be said about the relations between these two works, but I'm not going to get into it. There are then a sequence of results by Jeremy Szeftel and myself, and also by Shen. So these are results in 2018, 2018. And these are results on exactly the issue of gauge. So there are two major issues. One is treatment of the Teokolsky equations. Of course, you have to treat it in the nonlinear case, which is much more difficult than in the linear case. But anyway, that's one big issue. The other issue is how do you pick a gauge, right? And this somehow, the choice of gauge is what we call GCM spheres, which they already appear here in this work. And they also, by the way, the same kind of condition also appears here. So in other words, this is really a fundamental issue connected with the whole thing. Anyway, after that, the results on nonlinear stability of slowly rotating Kerr. There is a work that I done in 2021 with Jeremy. And then finally, a second part. So this was used, in fact, the results that were proved later on were used as a black box in order to do this. But this contains sort of the main ideas of the whole proof. And this contains somehow everything that had to do with the wave equation, which is, of course, extremely technical. But and, of course, there were lots of new ideas also. All right, so let's talk a little bit about the result. How much time do I have?
I think 20 more minutes.
Ah, very good. Okay. Here is the result. Okay. A little with a few more details. So this is called the future maximal global hyperbolic development. So this is a notion that is just an interpretation of the local existence result, how far you can go in local existence. So the future global hyperbolic development of a general asymptotically flat initial data set. So this is the initial data set that you put here. Close to the initial data set of a Kerr solution with A 0 over M0 much less than 1. has a complete future null infinity. So what does it mean? It means it's global, but it's global only in this direction. You are very far away from the horizon. There is a horizon which is put in red because it's defined only a posteriori, as I just said. This would be a point at time like infinity here, or along the null hypersurface. So this is a future event horizon. So this obviously happens at infinity. But this is infinity long. In other words, you can go, an observer that lives here can go forever. Okay? So it's global in that sense. Right? Of course, all these things can be made more precise, but intuitively that's exactly what it means. Obviously, for an observer moving in this way, you move into the black hole, and then obviously you are not going to leave any further, right? So it's not global in the usual sense, right? It's global only up to the horizon. In fact, a little bit, you can even go, as I said, you can go a little bit beyond the horizon. So the space-time, what's important is the space-time is constructed by a continuity argument as a limit of what we call finite GCM admissible spacetimes. Okay? So this is a crucial concept in all of this. This is where you choose a gauge, and this is where you do the bootstrap, and so on and so forth. Right? So let's talk a little bit about this. So here is what a GCM admissible spacetime consists of. Right? So first of all, there are boundaries. So let's look at the boundaries first. Right? So there is this boundary, which you should think about it as being boundaries representing the initial data. So you see its initial data represented. There are some complications which I don't want to get into it. If this was stability or Schwarzschild, this would be exactly null hypersurfaces, right? And the fact that you can go all the way to a null hypersurface starting before, right? So if you start from a space-like hypersurface, you can go all the way to a null hypersurface. This was an old result by Nicolo and myself. It's sort of similar to the stability of Minkowski space. It uses similar techniques. In fact, Shen, Shen gave a much simpler proof of that result. So that result now, instead of being, I don't know, 150 pages at the time, maybe 200 pages, is now maybe only 60 pages. Is that way here? Yeah, 60 pages?
80 pages.
80 pages, okay. Right, so you see things simplify, which is great. So this is, it's because of this that we can start with data like this, because you already assume that the spacetime can be constructed up to that, right? And then you have to go further. All right, so the GCM admissible spacetime has these boundaries, but it has also an apparent horizon boundary, which is beyond the horizon. So you see horizon here in red. So it's in the black hole region. It's a space-like hypersurface. This one is also a space-like hypersurface. Again, if it was in Schwarzschild, this region will not be there. This would be null hypersurfaces. So for simplicity, just forget about this region and think about the fact that the space-time will be like this, just to simplify. The most important thing are, of course, is this boundary here, sigma star. So this is a space-like hypersurface which has to be completely constructed, right? So it's what we call the GCM sphere. So this is a sphere here, a star. It's a GCM sphere. So in other words, a two-dimensional surface. And this one is a three-dimensional GCM hypersurface. So this is sigma star here. And then after you have that, you have to construct the spacetime. So this is the essential boundary. Everything is constructed from here. So you construct by transport equation somehow. I mean, if it makes sense what I'm saying, you go along null hypersurfaces, which will be sort of analogous to these null hypersurfaces. U is t minus r and t plus r in Minkowski space. In our construction, of course, they are much more complicated, but they will be equivalent to those. And then you construct also a frame associated to this sort of thing. So in other words, you construct the space-time together with a frame. So we construct the frame E3, E4, which you have to think about it as being a perturbation of the principal null frame in Kerr. Right? So in Kerr, you have this principal null frame, which, as I said, diagonalizes the curvature. So here, of course, you don't diagonalize the curvature. but you make it small. In other words, most components are small, and there are two components which are not small. Okay. Anyway, so this is the main things about the space-time. So now I have to explain to you how this is used. Right. So like in any nonlinear problem, you have a bootstrap, right? So you have your space-time, you have frames, you have functions u and u bar maybe, just like here, which obviously have to be constructed. The most important thing that has to be constructed is as I said here, so you make assumptions about everything that you have under the sun, and the assumptions will be that if the data is, let's say, of order epsilon 0, in other words, the data prescribed originally is of size epsilon 0, you make assumptions which are of size epsilon, which are of course much larger than epsilon 0. Right? And then you start proving estimates. So you assume that you cannot go any further. In other words, you assume that by this time, you construct the spacetime as a sequence by a continuity argument. You assume that the moment you arrive here, your bootstrap assumptions have been, they are exactly at the level epsilon. You cannot do any better. But of course, what you want to do is to prove estimates and show that, in fact, the estimates are much better. So how do you do the estimates? Well, so there are two major parts. One is Teokolsky equations. So basically, let me try to explain a little bit what that means. So the Riemann curvature tensor decomposes relative to this frame that I mentioned, decomposes in components which are we call alpha alpha bar. Right? These are called the extreme components, and then a bunch of other components here. Right? In particular, the components which we call rho and rho star, which in Kerr are different from 0. Right? So this will be different from 0 in Kerr. The other components will have to be 0 in Kerr and therefore are small. But they verify equations, and these are exactly the Teokolsky. So alpha alpha bar verifies Teokolsky equations. This was the major thing discovered by Teokolsky in 1973. That these equations in linear theory decouple from everything else. Right? So this was absolutely a major observation. And also, it so happens that in linear theory, these two things are completely invariant. Right? So relative to the gauge transformations that we discussed about, these are invariant. Of course, in nonlinear, what that means is that these depend quadratically, right? So of this epsilon squared, right? So of course, you have to work much harder. You have to have non-null condition and so on and so forth. But in principle, what you need to do is to give estimates for this. So you have to estimate the things. And somehow this type of estimates, of course, you'll have equations, let's say plus something like this, where here you have nonlinear terms. These nonlinear terms depend on everything that you have in your spacetime. So it depends on all the bootstrap assumptions. And you have now to prove decay estimates for both alpha and alpha bar, right? Which are improvements relative to the bootstrap assumptions you have made for these quantities, right? So the proof splits into two major parts. One is curvature estimates. It's not just alpha alpha bar, you have to do other things, but curvature estimates, which are hyperbolic in nature. And this is what we do in this paper with Giorgi. And then once you have good estimates for those, then you have to start estimating all the other quantities. So you improve, you show that these things are, instead of being O of epsilon, they are O of epsilon 0 now. So you improve for these ones. So now on sigma star, you have improved estimates for alpha alpha bar, but you also have the GCM conditions, which are of fundamental importance. So what does the GCM condition, so far I can't say too much, it's just that, you see, in principle, you want to start from initial data and integrate in this direction, right? To carry information from wherever you know that the data is small. But this doesn't work because you're integrating along against curvature. So you are losing decay if you do that, okay? So instead, what we needed to do, and this is maybe the major new idea in the whole thing, in the whole program, is that you want to start with a star where you have various assumptions. Certain quantities are small or are like in Schwarzschild, say. See, Schwarzschild, I mean, you have to think about this as being sort of far away in regions where Schwarzschild and Kerr are not that different, okay? So anyway, so these have to be specified quantities, which are exactly quantities like in Kerr. So then, therefore, this allows you to integrate exactly those quantities in this direction, going this way, okay? And if you combine, it just so happens that these GCM conditions that we have are exactly the conditions that you need in order to satisfy all the freedom that you have in the gauge conditions, right? Because the gauge conditions allow you to make various choices. But of course, it's a limited number of choices you can make. But it turns out that what we make there, the GCM conditions are exactly what you need, right? So you have these GCM conditions here, and then somehow using them, you can go and prove estimates on sigma star, so prove that all quantities on sigma star are well behaved. And then once you are quantities on sigma star, you can move in this direction. These are typically transport type equations, right? They are not hyperbolic anymore, right? In fact, the hyperbolic equations are really just they're just the curvature estimates, which are. Anyway, so this is roughly what happens. So you improve the estimates here, and then you improve them here and here. And once you have improved, the next big thing is that, well, okay, so now I beat the bootstrap. I have, instead of epsilon, I have epsilon 0 now, all the way up to these boundaries. So therefore, I can extend my spacetime by local existence type results now. So that's kind of a trivial extension. So I can extend beyond all this. In particular, I can extend beyond the sigma star. And now, of course, the extension, however, is not a GCM admissible spacetime anymore, because you don't have the conditions on S star and sigma star, right? Which as I said, they are crucial. So you have to construct now in the new spacetime that you have to construct an S star and you have to construct the sigma star. And these are exactly these GCM, these GCM papers that we wrote, right? Which allow you to construct exactly, and these are highly non-trivial, I should say. And there is a huge kernel. The kind of equations that you get are highly degenerate. I mean, obviously you have to use all the kernel. I mean, the kernel is huge, and you have to use, of course, all the gauge condition, all the gauge freedom that you have. All right, so this way you can construct a new spacetime, which is GCM admissible, and therefore you can go forever, right? So that's roughly how it goes. Structure of the proof, I already told you, so I don't think there is much more to say here. I mean, here I say a little bit more. There are all sorts of other things that you have to do, but anyway, after all this stuff takes quite a lot of pages, so you can imagine that there is a lot to be done. But these are roughly the idea. Now, what are the main new ideas? And I'll finish with this. So, I mean, there are lots of things, but if I am to sort of identify what are the main 4 ideas, I'll put number 1, this GCM sphere, the choice of GCM sphere. The reason for this is that it's highly non-trivial in many ways, in particular because as you make a choice here and you construct the sigma star, which is also highly non-trivial. This is what Dawei has constructed. I mean, we had this in the Schwarzschild paper, and he generalized it to what we need for the Kerr result, for the Kerr papers. So you have to construct the sigma star all the way to this region here of the initial data. But now, you see, on the initial data, you have certain assumptions, which are assumptions expressed relative to a foliation, right? But when you come down all the way, you have you don't really you are not coherent anymore with the old foliation, right? So that's sort of, in a nutshell, this is sort of the main difficulty, right? Because you are starting from infinity, you are now, it's very, very hard to connect to the conditions that you have on the initial data. And in fact, it turns out that there are sort of major discrepancies. I mean, that there are certain quantities which measures the differences between the foliation induced from sigma star and the old foliation, which are all of 1, right? So they are not small. Okay, so anyway, so this is one of the major difficulty, and therefore I put it as number 1. The choice of the last slice, again, this is the sigma star that I mentioned. The fact that the structure that you are using is non-integral, this is a major problem, because in the stability of Minkowski space, for example, you have a frame which you are using, which is integrable. It corresponds to sphere, right? So it's compatible with sphere foliations. And because that means that you can do a lot of elliptic theory on spheres, right? There is a lot of Hodge theory that is embedded in all this stuff. Therefore, elliptic theory really lives naturally on surfaces. But now, in the non-integrable case, this disappears, right? You don't have spheres, right? So you have to do something else. So this is, again, a major difference. Control of Teukovsky perturbation of Kerr, that's another thing. How much time do I have now? I think I'm done, right?
You have a couple of minutes left.
Couple of minutes left. Okay, so maybe I can go a little bit into discussing this, because that's also very interesting. So general covariant modulated spheres, is too much to say, so I won't be able to say. Choice of the last slice, right? So again, this is the issue of gauge, which, as I said, is clearly the most important part of the whole thing. Lack of integrability. You have to rely on different foliations. So the major foliation that you are using is not integrable, but you can construct a different one, again using the frame, using the fact that the gauge group that you can use, the freedom that you have with a gauge group, to construct a new foliation whenever you need it, to construct a new foliations where you can do elliptic estimates. By the way, we have, this requires a sort of a geometric treatment of this horizontal structure, which replaces in the well-known Newman-Penrose formalism. So Newman-Penrose formalism was the sort of thing that was used by physicists. It's not going to work here because I think Thibault will have to agree with me. The problem is that in the Newman-Penrose, you have a lot of coefficients which are not geometric, and which depend in particular on the axis. They are, the moment you start taking derivative of them, you get singularities on the axis, and they are very hard to remove them. Okay? And with this formalism, you don't see those. You never see the axis at all. Right? So somehow it's better adapted to the kind of problem that we want. And finally, the control of the Teukovsky equation. So I mentioned that the Teukovsky equation was treated in Kerr, was treated by various people, but it was still based on Fourier methods. So in particular, Daniel had a sort of very beautiful treatment in his paper with Stojananu, but it still uses Fourier transform, and we wanted something that does not, and which is more compatible with the vector field method. So the advantage of the vector field method is that it adapts. I mean, you do it in flat space, in Minkowski space, or in Schwarzschild or in Kerr, and then it adapts very well to perturbations. Okay, so the same thing here. Well, first of all, there are all these issues that I'm not going to get into this. But the way in which resembles the vector field method is that in Kerr, you have some symmetries which are given by the vector field T and vector field Z, if you remember. These are the vector fields which are killing, right? So they correspond exactly to axial symmetry and to time translation symmetry. And of course, they have good commutation properties with a wave operator. Even with this has good property even with a Teukovsky operator. So I'm talking now about the Teukovsky, which is more complicated. What the remarkable thing about Kerr is that there is another operator which is not a first order operator, which is called the Carter. It's a second order operator which commutes, right? So it's a second. So this was a discovery made by Carter, also in the late 60s, I think, and was used for integrability issues, the integrability of the geodesic flow on Kerr. It's used on all sorts of things. Here is the first people who have actually used this for getting estimates for solutions of the wave equations were Anderson and Blue. So Anderson and Blue use this in the particular case of just a scalar wave equation in Kerr for small angular momentum. So what we did is to adapt this to perturbation of Kerr. So I mean, this is one of the major technical issues that unfortunately takes a long time to develop. And again, I do hope that all these things will get simplified with time. I mean, the papers are long, but almost everything on it, I can see that they're going to be simplified quite a bit. So maybe I'll finish.
Thank you very much. Are there questions? Comments? Okay, so maybe I'll start. There's something that I missed, I think. When you use this modulating... Oh, sorry, I didn't...
Yeah, he will take
no.
Okay, so if I understood well, probably was here that you use really the smallness in this...
yeah, okay, so the smallness of A, you mean? The angular momentum.
Yeah.
The smallness of the angular momentum. Yeah, it's really the wave equation. I mean, basically, you don't need the smallness of A for just about anything except the wave equation, right? So the wave equation. So, for example, I mean, here is, I think I'm not wrong if I say that. If we knew how to extend these methods based on the Carter operator, if we knew how to extend it to Kerr for large A, then I think we would be able to do the whole thing. So in other words, everything else doesn't seem to depend on the smallness of A, except everything hyperbolic, everything that is to do with the wave equation.
So are the value of A infinity and M infinity like continuous with respect to the perturbation? And also, in some sense, can I impose two conditions on my initial perturbation so that they are equal to the initial values?
I'm sorry, say it again, to impose two
conditions on my initial perturbation,
yes.
So that A and M does not move.
Yes, that's one of the results, which I didn't mention, of Dafermos, Holzegen, Rodniansky, and Taylor. They are able to find a posteriori conditions. So again, you don't know a priori what they are, but they can show that there exist conditions. So it's a codimension 3 set of conditions, so that if those conditions are satisfied, then you still converge to Schwarzschild, right? So they wanted to do it in such a way that they don't move. I mean, Kerr is much more complicated for all these reasons, but right. Yeah, so there are conditions. Of course, our condition, we also had conditions. Our conditions were slightly, I mean, were more stringent. We use polarization. But they do effective, I mean, from a technical point of view, it's really no difference. I mean, if you know how to do polarization, I don't think, I mean, some people may disagree, but I don't think there's much difference between polarization and the case where you have this.
For the mass, you cannot fix it because you lose mass at infinity.
Yes, right. Right, so when you do Schwarzschild, the mass, of course, has to change. Right, so you can keep A to be fixed, 0, and you can change. Right. You can change the mass has to be changed.
Other questions?
Sorry. In one of your slides, there is a remark, and you touched a bit on that, but could you elaborate, please? You say that the gauge is fixed from the future with no reference to the initial data.
Yes.
So how do you...
How do you do that? Yeah, that's a good question, right? So, right, so it's here, right? So yes. you make all these conditions here, right? So think of the construction. So let's say the spacetime has already been extended and you have to find the newest star, right? But the newest star is here, is far away from the initial data. So you have to impose conditions far away. It's a codimension 2, so you have to construct a codimension 2 sphere. Everything else, by the way, maybe I should say, everything else in the literature before, like instability of Minkowski space, was based on constructing foliations, let's say spheres, on a given three-dimensional hypersurface. So it would be a codimension 1 sphere that you have to find. And usually those spheres are connected to the initial data, right? So you are starting from the initial data. When you construct these things, you are starting from the initial data. And you construct it here, it's a codimension 2, so it's much more difficult from a geometric point of view. And again, I mean, you have to construct it far away. I mean, a priori, you don't have any connection with the initial data. So you have to find a way to connect it, but that's technically difficult. So I think psychologically, this was the main reason why this kind of gauge fixing was not used before. It's also codimension 2. It's much harder. The codimension 2 case is much harder than codimension 1. Codimension 1 was used now for many other problems in general relativity.
Other questions? So I think you partially answered the one that I had, but just to make sure, so you use these modulated variables, I guess, to find the final phi f and af, right?
Yes.
Do you also use it to find what the correct gauge is?
Oh, absolutely, yeah. That's the whole thing. I mean, so that's the whole point, right? So when you construct the space, when you extend the space-time, you have to find a new gauge. The gauge is going to be different. So every time you extend, you find a new gauge, right? So the gauge is not defined from the beginning.
And the two parameters from the finite cone that I mentioned, you
Also.
find them, so
the same thing, yeah. You find them together. In fact, it's connected to this GCM construction, right? Which is also, by the way, the GCM construction is also very pretty. It's one of the things I like about, as it's very geometric. So it uses a uniformization. It's based on a uniformization theorem, which is an effective. I mean, the problem with uniformization for spheres is that it's a highly non-unique phenomena. When you find a uniformization, it's highly non-unique. But fortunately, there is a notion of effective uniformization, which allows you to actually get the correct uniformization map. Anyway, there are a lot, but yeah, sorry.
Other questions? Okay, well, thank you very much again.